learning. We finished double integrals, I believe, last time, right? We get to look at the triple integral. And as before, we're going to define it in terms of over a rectangular box. And so again, a rectangular region is the easiest region. And it is now the limit of a triple Riemann sum. Again, we're not going to actually worry about ever using that definition, because that definition is definitely a pain to work with. So instead we move on to Fubini's theorem for triple integrals, which tells us how we're actually going to go ahead and evaluate a triple integral. Again, for a box, AB cross CD cross EF, the integral over that box is a triple iterated integral. It's the integral from A to B of the integral from C to D. I'm going the other way. Integral from E to F of the integral C to D of the integral A to B, f of x, y, z, dx, dy, dz. Or any of the other 5 combinations of the orders. So the order doesn't matter. So again, double integrals, we evaluate by setting it up as an iterated integral, and then use the fundamental theorem of calculus. In that case, twice, right, because it's a double integral. Triple integrals, you set up the exact same way. It's set up as an iterated integral, triple iterated integral. Then we use fundamental theorem of calculus 3 times. Over a general Cartesian region, right? So let's say that E is our 3-dimensional region. In this, again, in this case, we call it solid. Right? So for 2 dimensions, we call it a region. 3 dimensions, we call it solid of integration, but it's still a domain of integration. Defined as set of ordered triples, x, y, z, such that the ordered pair xy is in some 2-dimensional region D, and z is between 2 functions of xy. Right, this 2-dimensional region D is the projection of your solid onto the xy plane. So if you will, kind of like the shadow of your solid on the xy plane. Then the integral over E, notice that now the differential is dV. It's a volume differential now.
Wasn't it dV? On the last slide, wasn't it dV?
Yeah, I'm just mentioning it here. Right, so for triple integrals, the differential is now a volume differential. So that integral is going to be the integral over your projection D of the integral u1 to u2 of the function dz dA. And then, of course, we know how to do the double integral. pictorially, this is what's happening. Now again, with this, they set it up as, oops, went too far, DZBA. Doesn't have to be. Right, you could look at a projection onto, for instance, the YZ plane, right? And then have X be between functions of Y and Z. Then you have DXDA, right? So again, the order doesn't matter. It's going to boil down to how you're going to set up the region, how you're describing the region. That dictates the order that you're going to use. By default, the easiest order to use DZ, DY, DX. And that's typically what we'll use. What was the geometric interpretation of a double integral? So you integrated a two-variate function over a two-dimensional region. What was that geometric interpretation? So at single integral, the geometric interpretation was a signed area, right? So what is the interpretation for a double integral in terms of geometric quantities?
Of volume.
More specific.
Like a volume over like the area.
Right, it's not just a volume, it's a specific type of volume.
Up to like the surface. Oh.
Sign. Positive if it's above, negative if it's below. Okay, remember, volume itself can't ever be negative, but a double integral can be, so you have to specify it's a signed volume. Much like single integral is a signed area, right? So then what's a triple integral? What do you think?
Volume over the duty surface.
It's a signed hypervolume, right? The four-dimensional equivalent of volume. Positive if it's above the XYZ, negative if it's below the XYZ. And I use quotes because it's not above and below in the tip in the sense that you think of. It's above and below in the fourth dimension, which you can't visualize.
So how do you see it?
You don't. It's impossible. We know it exists. Math. Right. That's the good thing about math. We can just say it exists. We define it. So what you have to do is to get the fourth dimension. It's the same way we got the third dimension. Right? It's the same way we got the z. We just drew an axis that was perpendicular to both x and y. To get the fourth dimension, you do the same thing, except it's now perpendicular to all three. So that direction is, by definition, the fourth spatial dimension. but you can't visualize it.
And how many dimensions do we have to it? Four.
Are you talking about theoretically? Theoretically, there's an infinite number of dimensions. Because you can just keep going, right? Fifth dimension, now just draw an axis perpendicular all four. That direction is your fifth dimension. Sixth, so on and so forth. In terms of reality, for most applications, 3 spatial and 1 temporal. But time doesn't fit into this kind of dimension system that we're talking about, like drawing an axis. We don't really think of the time axis in terms of the coordinate planes. There is a time axis, but it works differently. According to string theory, there's 9 spatial. Plus 1 for time. But string theory hasn't been proven. I don't want to say proven, you can't actually ever prove scientific theory. Hasn't been verified physically. It's been proven mathematically. The math works. But we just haven't been able to actually verify that it is true. Like, are there actually 9 spatial dimensions? We haven't actually verified that. And I don't think we're ever going to, because of the magnification required and the energy required to do that. But the math works, so we just go with it. And actually, this is what your project is on, isn't it? Volumes of hyperspheres. So I think it starts off with the 2-dimensional hypersphere, which is just a circle. Then the 3-dimensional hypersphere, which is just a sphere. And then they ask you to go up to what, 5 before making a generalization or something like that. Maybe it's only 4 and then a generalization. Well then, what would that give you?
The volume of the object.
Which one?
Oh, W? Because it would be the 4th dimension.
Volume of what? You're overthinking it. What are you integrating over?
The function.
That's what you integrate. What are you integrating over? What's your domain of integration?
Is it not the 4th? Like,
Thanks for that.
is it not W?
In this case, E, we also use W. But it's just the volume of whatever the region is that you're, right? It's the volume of the solid that you're integrating over. So now we have a way to calculate volume. That's not a double integral, you set it up as a triple integral. But I think this is what the project is. You're not actually integrating a function, I don't believe. You're just trying to find volumes of the sphere. And remember, you have your area, and your length. So just about every geometric measure is an integral. Right? Length, area, volume. And if you continue going in that sequence, right, hypervolumes, they're also level integrals. Oh, by the way, When you're dealing with 3 dimensions, you do get a new geometric measure. Surface area. Right? Instead of looking at the volume as a whole, you just care about, okay, well, what's just the surface? Surface area, that's also an integral. We just haven't studied it yet. We will study it in the next topic after exam 2. That's also an integral. And average value of a 3-variate function over a solid. 1 over the volume of the solid times the integral over the solid of your function dv. And just to relate it to your other 2 average values. Just notice how they're all related. They just go up a dimension each time. Which means you should easily be able to see what the average value of a 4-variate function would be. So to start off a little simple, we're just going to look at a triple iterated, evaluate that. And we don't actually ever do a box, it doesn't look like. Oh, we do, it's just for average value though. And so start off with the iterated, the triple iterated, and then we'll move on to actually setting up an integral as an iterated integral. The idea is the same though. So the outer integral we do last. So integrate with respect to x last. This is how the nesting would work. That innermost is always done first. We're integrating with respect to z. So z is the only variable that's changing. xy held constant. Antiderivative of z
Z squared.
Go ahead and just factor out that 1/2. Let's not expand that out just yet. Well, now we have to integrate with respect to y. The x and the 2 minus x quantity squared, they're both constant with respect to y. That means we're only doing the antiderivative of y, which is y squared over 2. Now use fundamental theorem. Bummer. We're going to have to expand. This. 1 minus x quantity squared. How does that expand?
1 minus 2x plus x squared.
1 minus 2x plus x squared. How does 2 minus x squared expand out? Now we get to expand that. Do we want to go in ascending order or descending order? Of x.
Left to,
Ascending.
yeah.
Ascending?
I just did from left to right on the first one.
Yeah, I'm going to stick with ascending simply because that's how it was given. Even though I prefer descending. 1 times 4 is 4 times x. That's the only first power of x we have. Okay. We're going to have, it looks like a minus 4x and a minus 8x. That's minus 12x times x. So minus 12x squared. X squared plus 8x squared. And then we're also going to have this here, right? Plus x squared plus 4x squared. So That's 5, and 8 is 13. Another 13x cubed. Yeah, plus 13x cubed. Look for the x cubes. There should only be 2 terms for that, right? Minus 2x cubed, minus 4x cubed, minus 6x cubed, times x, minus 6x to the 4th, and then plus x to the 5th, right? That's where we should be at. That's not too terrible. That should be an antiderivative. And the fact that it was 0, 1 makes this even better. What is that LCD? $60. Oh joy. Fractions is just so much fun. And so that's going to be 120 minus 240. And that's what, 13 times 15? 150, 45, 195. That's going to be 12, so 72. Plus 10. And that's 130. 130 and 195. 325. Well, I'm just doing the addition right now. 325 minus 240 minus 72. I do agree it's 13. Thirteen over 240. And then you just erase your scratch work. And go, it's obvious. Okay. Again, none of these concepts should be new. For this one, that was all just Cat 1. We just did it 3 times. The issue comes when you have a really complicated integrand that requires like Count 2 techniques. You get like a partial fraction in there, and then you have to do trait sub somewhere, maybe an integration by parts with another partial fraction. You'd spend like 3 hours on a single triple integral just to get 0. You laugh, but in physics you celebrate when you get a 0. 0 is really nice in physics. It means you did it right. When you get an infinity, you know you did something wrong. Then you cry. Oh, that's nice. This is a rectangular box. I'll call it a cylindrical box in this case because it's clearly cylindrical coordinates. That means the order in which you do this does not matter. Right? We can flip this however we want because it is just a box. Which would be better to do first? Maybe get rid of that sine theta. So just integrate sine of theta from 0 to pi over 2 first. That should be 1. Right, negative cosine theta is your antiderivative. Cosine of pi over 2 is 0, cosine of 0 is 1, so you get negative 0 minus 1. Break that out. Z is probably the next easiest one to do. Z squared over 2, we divided that from 0 to 2. Z squared is 4 over 2. We should just be left with 2 times integral 0 to 1 of r squared dr, right? R cubed over 3. I forgot to do though. Just get 2/3. Hopefully that one was nice and easy.
I'm still a bit confused. When will the order matter and when will the order not matter?
Technically, order never matters.
Doesn't matter?
You just have to describe the region.
Okay.
When it's a box, which means all of your bounds are constant, you can just freely change the order without redefining the region.
Okay.
Unlike here. Well, there's a bit of good news though. None of your bounds depend on theta. Right, but rho depends on phi, which means you have to integrate rho first before phi. But theta can be done whenever we want. Is there a theta in the integrand? No. Integral 0 to pi of just d theta, pi. Well, that's nice. At least we cut our work by a third. But now we have to do with respect to rho. But there's no rho in the integram, so that's also a relatively simple integral to do. It's just seeking a phi, right? Now, how do we evaluate that?
Wait, I don't get how you evaluate that, because you don't have a rho.
Right. So if you integrate just d rho, that's the length of the interval. Secant phi minus 0, secant phi. That's how I got it. It was the same thing as with the theta because there's no theta in the integram. It was just the length of 0 to pi. So how do you think we're going to go about evaluating this?
You said,
What would your U be?
cosine?
Then what's your DU? Your U is cosine, what's your DU?
Sign, or I guess negative sign.
Is there a negative sign of phi?
No.
Is there a sine of phi, d phi?
Yeah.
Where?
Oh,
Sorry,
no.
2 feet.
Sine of 2 phi. So that U wouldn't work. Once you see it, this is actually a really, really easy integral.
Do you change the sine of 2 feet
To what?
to sine of phi cosine of 2?
Mm-hmm. 2 phi is a double angle, isn't it? So sine of 2 phi, double angle identity. 2 sine cosine. But secant's 1 over cosine. Secant times cosine is 1. That's what you're left with. What is the antiderivative of sine? Evaluate that from phi 0 to pi over 4. What's cosine of pi over 4? It's cosine of 0.
Oh, 1.
Or if you want to write as a single fraction. So that would be 2 pi times 1 minus root 2 over 2, or 4 minus 2 root 2 pi all over 2. Want to integrate z over the region in the first octant, bounded by the planes y equals 0, z equals 0, x plus y equals 2, 2y plus x equals 6, and the cylinder y squared plus z squared equals 4. Let's try and get a visualization of this region. So we have y equals 0, z equals 0, x plus y equals 2, 2y plus x equals 6, and then y squared plus z squared equals 4. We know in the first octant, so let's do this. I may need to adjust that. Turn off the mesh, turn off the box. Origin. I set the opacity to 0.5. Makes it easier to see through it to get a better idea of what the three-dimensional region is. Shift enter. Expressions and set a viewpoint. Good, I don't need to adjust it. Let's just see if we can rotate it a little bit. Get a better idea of what we're looking at. That should be good. Although it does look like I actually do have to go out a little bit more. It's a little bit better. Let's say that. That's not now connecting. Oh my goodness. This plane should intersect at some point. Oh, I don't think I need them to intersect. No, I don't. All right, so this will work. And here's the solid. That is our solid with integration. And so it goes between these two planes. Then from this plane that's coming out to, I think, this plane, to the cylinder, and then up from the x-plane up to the cylinder. So now we have to try and describe that. What I can do is try to shrink this to make it easier to see, maybe go down to, drop the z down to 3. The x maybe to 6. y to 3. Yeah, that works. That's a lot easier to see now. If I do this, down, it is this entire solid under the cylinder. That's the region we have to try and describe. I want to get a really good view of it that shows everything. Maybe like that. Is that a good feel? Right, so if all order triples x, y, z such that, so how do we want to describe this? Z is easy to describe, right? Because Z, remember this is the Z axis. Going from the plane, Z equals 0, up until the cylinder, right? Z squared would be 4 minus y squared. Because we're above z equals 0, that would be the square root of 4 minus y squared. So that was relatively simple. This is the x-axis. That might actually be the second easiest one to describe. Because that's just going between two planes. Right, the green plane and the red plane. Whereas we tried to do y, y would actually split. Right, because y looks like it would start from the cylinder to the green plane, it actually looks like first. Then it would go from the cylinder to this back plane. And at some point, it looks as if you go from the red plane to the back plane. So that's 3 separate descriptions for y. That's just hideous. But x is just always going to be between two planes. So yeah, let's do X next. Now what is the increasing direction of X? This way. So the green plane would be the lower bound, the red plane would be the upper bound. So lower bound for X, we want to write the green in terms of Y, 2 minus Y. Upper bound for X, right? This red plane in terms of Y, 6 minus 2Y. Yes. And now Y is going to be a constant. The bounds for Y are going to be constants. So the region looks like it goes from 0 out to 2. Right, that's where the cylinder cuts off on the Y. Next. Remember, once you get Z, what we're really doing at that point is now look at the projection of our solid onto the XY plane and then describe that new domain.
Right, how can we visualize a zero district?
Right, so this whole thing's in the is the region, right, underneath that cylinder. So what does that extend across on the y-axis? Clearly starts at 0, right, because it starts at the y equals 0 plane. And it would come out until that cylinder hits the z equals 0, right? Where does that hit? At 2. Right, so this is a straight line at 2, y equals 2. So that's why it goes 0 to 2. You could also just visualize, do the projection of this onto the xy plane. You don't have to make one change. Obviously, this would be deleted. In here, you just put z equals 0. You get y squared equals 4. So y equals 2. Because we're in the first quadrant. And you just plot all of these back. And you can get a bunch of lines. And then from there, you should easily be able to see how to describe your projection, which is the x and y. And actually, let's, I didn't. They're going to be a pain to fix now. That's annoying. I'm going to try and do that. Next, I'm going to literally just plot everything, replacing z with 0. I'm going to keep my x and my y's the same. X goes 0 to 6, y goes 0 to 3. I'm actually not going to do that. I'm going to go a little bit. Just a slight bit to the left. And a slight bit below. I can't be bothered to change default colors. This would be the projection, right? X goes from yellow to the green, and then Y would go 0 all the way up to 2. Does that make more sense now? So that's what we were doing. I just didn't actually plot out the projection. But once you pick your first variable that you want to integrate with respect to, in our case we did Z first, then you just, so in the case Z, set Z equal to 0, you can then replot it, that would be your projection, with ZB equal to 0. Then you just have to determine, okay, which of this is actually the projection. Fairly simple to see which one's the projection. So we wanted to integrate over the region W, the function Z, right? So that is the integral we're looking for. The way that I have it written, we're doing the Y last. So your outer bounds are for Y. Middle bounds are for X. And then the inner bounds are for Z. That would be the iterated integral. So that is what we have to evaluate. And I think that is what we'll pick up on Thursday. Because this question, so we have to evaluate that, and I just have one more question. I don't know, 2 more, but they shouldn't be too difficult. Questions on the triple integral so far? The setup is even more of a pain than the doubles, isn't it?
Are we going to be given like a graph on the test?
Depends. For something like this, I'd probably give you the graph. For a more simple, solid, I probably won't.
Like if it's just like a triangle or something. Yeah.
And so if it's like a three-dimensional triangular region, yeah, I probably won't give that. But for some really complicated ones, I probably will.
Okay.
So what we got coming up? Now, yes, no more of this stuff is up. It won't be due until the 10th, and don't forget, second exam is this Friday. If you haven't picked up that reference sheet yet, that you're allowed to write your formulas on, make sure you do that before you leave. See you Thursday.